So this is class number 3, and we're going to talk about the importance of the atmosphere. Atmosphere is a very, very important quantity in aerospace analysis. Atmosphere is where the air exists, everything above, you got the earth, everything above the earth, where the plane is going to fly from the takeoff to where it's located. you got you got planes that fly within our atmosphere, outside the atmosphere, and different types of cases. So there are a couple things that we need to keep in mind. And so let's go back to our board. Um, First of all, when we talk about the atmosphere, you have to keep in mind that typically it is constantly changing. It changes from typically changes from day to day, and the reason for that is one day it may be very cold, another day may be very warm, one day may be raining, the other day may be snowing. So this is going to be changing as we go along. It is important to aerodynamics, is important in the study of aerodynamics because everything is a function of many of the parameters that we work in the study of aerodynamics itself. Let me give you a couple examples. Like for instance, many stuff that we do, they're a function of length, velocity, viscosity, which we will talk about today, density, temperature, uh, pressure, and the list can go on and on and on and on. So that is important. Then another thing that is very, very important that we will talk about today is the density. The density is a very, very important quantity and is typically a function, the density is a function of pressure and temperature. Okay, so this is pressure and this is temperature. So you can immediately see that given the value, different temperature, different pressures are going to give me different values for my density. Another term that's very, very important is viscosity. And viscosity is a function typically only of temperature. So there are many equations that we can probably use to study this that can help us to better understand these aspects over here. So, so if I'm going to define, first of all, viscosity, you know that typically, so when I have viscosity, viscosity is a function, in general, is a function of the gas. Here in this problem, the gas that we are interested is air, but that's what we are trying to do. Is a function of the temperature and pressure. Okay. And so for most of the viscosity can be, you can approximate viscosity using the following equation. 10 to the minus 6 t to the 1.5 divided by t plus 110.4. This is for gases with a temperature less or equal than 3000 Kelvin. Okay, and if it's less than 3000 Kelvin, it doesn't, the viscosity does not depend on pressure. Okay, so for that range, this is perfectly valid. Okay, with that said, let's see some equations that are important that we'll be using throughout the class today. Before we go to the equations, let's go and understand what the atmosphere look like. So one of the things that you have to keep in mind that when you do this is where most of your this is your troposphere, stratosphere, mesosphere, thermosphere, exosphere. Okay, so all these satellites are typically here uh, in the exosphere. So if I have a satellite, this is the location where they will typically be. The thermosphere is very, very hot. It's typically where your space shuttles or your space shuttles will go, or spacecrafts. That's where they will fly. The mesosphere is a very cold. This is a cold. Right here is very cold. So this is refers to this. And then stratosphere is where your jets fly. Okay. Typically, your airplanes. This is where your military aircraft may fly, but typically here, somewhere between here and here, this is typically very close to here is where uh, your uh, your airplanes fly, like a Boeing 787, etc., etc. Okay, so if I look at a typical temperature distribution, a typical temperature distribution is going to look something like this, where here this is the altitude. So this is as I go in the height, where you are talking, this is sea level. At 0, this is sea level. Okay, and this is where your jets fly, typical jet streams. This is where the jet streams are, and in this particular equation, sorry, in this particular table, what we can do is we can take this and we can zoom this section right here that becomes very, 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 very important. Um, and this section right here, I'm going to zoom that out. This is in Celsius, okay? And I'm going to convert this plot in kelvins and have this H in kilometers, typically. And usually, typically somewhere here at 11 kilometers and 25.1 kilometers, you have a complete straight line. This value is close to 220 Kelvin. And then you have a straight line that comes down here, and that point right there is 288 Kelvin. And then you will have this slope. These slopes are kind of the same, they're inverted. So typically, if I want to fly, this is a very hot spot where you may want to fly. So what you have is a typical aircraft maybe flying a plane can be flying here, let's say a typical Boeing 747, maybe a supersonic aircraft like in the old days that you had the Concorde, they fly in this region over here. I'm sorry, maybe lower than that, somewhere over here. Um, and nowadays they are trying to redesign this with new, um, they are trying to redesign this with new specifications. So this right here is nothing else than 1 over a, and that will be kind of like inverted slope right here. It's the same slope. So if I am going to explain how this relates to this, I'm going to change the colors for a moment. This section right here is troposphere. This right here. And then this section, and on, that would be this guy over here. Okay. For our interest, this is the region that we mainly are very interested in, because this is where your flight is going to be at. This plot is very, very, very important. It tells you how the temperature varies with the altitude, right? There's a region that's kind of constant. This is region where it's a linearly dependent and it changes in its values. And those are the, and we can see, as I mentioned before, that many of these quantities are temperature dependent, right? So if this is changing, you can see that your density is going to change because your temperature changes. In this region, you can know that maybe your temperature is kind of constant, your density is constant because the temperature is constant. So your book has a couple of nice charts. Those charts, table 1.1, let's say, that particular table basically tells you different how to find the viscosity for different temperatures. This is the viscosity for many temperatures. So typically what we do is we come in this table and we will find the temperature that we have. We may interpolate. Once again, I just wanted to go over the interpolation. I know we went this in a simple example. The interpolation consists in the following. So if I have a line, I know a value here, okay, let's call that value x1. I know a value here, let's call that value corresponding value y1. I have another value here, let's call that value x2 and y2. Now, I want to know what is the value y if I knew this value, let's say x3. So I am very much interested to know what is y3. In order to do this, we can use the slope equation. This is linear interpolation. Linear interpolation. We use this very, very, very much here in, when we use these tables. And assuming that linear interpolation is valid, what we can do is, we know that your slope equation typically is y is equal to slope x plus your intercept b, right? So the problem reduces to find these values. So the first value, your m is nothing else than x2 minus x1 divided by y2 minus, oops, sorry, got this the other way around. Again, y2, y1, x2 minus x1, okay? Okay, that's how we find the slope. And then in order to find the intercept, we can put the slope back in here. These are all numbers now. We know these numbers. And we can use any value that we want. Let's say I use x1. I can put x1 there, and then plus b, and I can solve b. So b in this sense would be y minus y2 minus y1, x2 minus x1 times x1. So now that I have my b, I have my m, I have an equation for that, right? So if I have the equation, now I can find the unknown value I want. Let's do an example. Uh, a very quick example, just so you can understand how this works. So let's suppose I have this, and I want to find what is the value here at 500. Okay, 500K, I would like to know what the value of mu is. And I know these two values. So I want to find mu. Okay, let's suppose this is my y. So the equation actually looks like mu is equal to mu2 minus mu1 divided by temperature 2 minus temperature 1 multiplied by T plus B. Okay. So your moment, your slope would be between these two values. This would be 2.992 minus 2.272 divided by 600 divided by 400, and that gives you a value of 0.036. So now you have mu equal to 0.0036 times temperature plus your intercept. To find your intercept, use either one of the values. Let's say I'm going to use this value, 2.992. 0.00036. Again, I'm using this value right here, multiplied by 600 times our intercept b. So b will be equal to, so the value is 0.832. So that would give you a value for that means your new equation then will be mu is equal to 0.0036 multiplies T plus 0.32. That means if I knew my temperature here, then I replace that and I can find my mu. So for our particular problem, we know that your mu will be 0.0. This is the mu I'm interested over here. Okay, for this particular value, 500K. So 0.36 multiplied by 500 plus 0.832, and that would give you a value of 2.632. And don't forget, all these values are multiplied. These are all these were multiplied 10 to the 5. So this value is 10 to the minus 5 kilograms meters second. Okay, so this is minus 5, cannot be plus 5. It doesn't make sense. Okay, so that's how we do linear interpolation. Just a quick review in case you have never seen that. Then we also have various atmospheric pressures for different altitudes. You can go and find different pressures, temperatures, densities, viscosities, and speeds of sound as well. Your speed of sound also changes with height. Um, so this is a typical value that you know at sea level. Anytime you see zero, we are talking about sea level. And this table continues here, uh, more from up to 20 kilometers. And if you just remember, we are basically interested up to about 20. This is where we fly. Okay, we can go up to 25, but 20 is okay. So that's why this table goes to 20. We also have its counterpart for SI units. Now in the SI units it goes to 40 because that's the conversion for that. Um, so this is how atmospheric pressure quantities actually work. Okay, so with this said and done, um, there are a couple more things that we need to understand how atmospheric pressures work. Let's suppose this is the absolute pressure. In this particular case, we talked about this, that this is the absolute pressure from the sea level. This is zero pressure. Then this is your negative gauge pressure, positive gauge pressure. This is atmospheric pressure. This right here, the atmospheric pressure, and this absolute pressure is less than the atmospheric pressure, and then this is greater than the atmospheric pressure, just because you are positive and here you are negative. So when you have, this is reading the gauge, is reading your delta P, is reading this difference, but your gauge is reading this delta P, then it's reading this difference. And this is important, but this is the absolute pressure minus your atmospheric pressure. Okay, so with that said and done, let's continue with our discussion now. What are the equations that we actually need? We need a couple of equations so we can understand this whole thing. So let's go back to my black marker. So for the case of we know a first equation we talked about last time is the ideal gas flow equation. The ideal gas flow equation says the pressure is equal to the density times my gas constant times my temperature. Okay, this is an empirical equation and it was derived for ideal gas. Also, we know that for the case of hydrostatic pressure, the hydrostatic equation is given by the following equation. Okay, minus rho dH. Okay, to better understand what is this, the hydrostatic equation especially, let's go ahead and derive this equation for you, where it comes from. So if I had, this is your ground, okay, this is your height, h is your height, and if I took this now and I took a small segment right here where this is dH, it's a small differential dH. So this d is not a distance. This is talking about differential. Okay, it's like talking about delta P related to delta H. So instead of using that, if I make this delta very, very, very small, then I can make it delta H and I make it this delta P. So what I basically want to do is, this is whole air, and let's suppose I want to just take a small cube of air. Okay, so I want to take a cube of air, okay, or maybe just take an element. Let's call it the element of air. So it's not, you don't think it's all distances are 1. Okay, so in this element of area, element of air, we're going to consider this is an element of unit area. So if I take this element and I draw it again, my element is going to look something like this. So I have pressure at the bottom, P, and then I have a delta delta H, the difference. And what you can immediately see that I'm going to have the same pressure plus some differential pressure that's acting on there. Okay. So what I'm going to have is areas at the top and the areas at the bottom. This is area, element area. So the differential equation then is going to relate to the variation of P. Is going to be a function of the variation of H and the local value of P, rho. This is what this equation is saying, and this basically comes from here. Consider this. If I take a sum of forces in this direction and make it equal to 0, a static case, so what you will have is you have positive P minus P plus dP, and this is minus rho g dH, okay, equal to 0, because this is also gravity acting on this, but this has a mass. Remember, this element also has a mass, and because it has a mass, it's going to have some weight, and we are doing weight per unit area. Okay, so this differential equation, then your P and P cancel out, and you can show that your dP is equal to minus rho g dH. So this is the equation that we are going to use, and this equation actually tells you any change in this is going to depend on the change of height, which also depends on change in my value rho. Okay, so that particular equation, if you realize, let me write it down again for completion. This is nothing else than a differential equation. This is a differential equation, and this differential equation relates the variation in P as a function of the variation in H and the local value of rho. Okay, we are going to assume that your gravitational constant remains the same. Okay, it's a constant. So for small deltas in H, your G doesn't change that much. Okay. So the properties now, if I'm interested in, let's keep moving on. We also know that from your ideal gases, we know that P is equal to rho RT. So what I could do is I could say del P dP minus rho g dH, and I could divide both sides by P, But now just realize that your P, I can put here nothing else than rho RT from here, from the ideal gases. Okay, so by doing that, then your equation now becomes dp rho is going to, and rho cancel out, so end up with g over RT times dH. Okay, so this equation has different ways of solving it. First of all, you have to know this equation becomes very easy to solve in this region over here. As I mentioned to you previously, your variation looks something like this, where this region is 11 kilometers, and this is about 220 Kelvin. From here to here, this is the stratosphere, okay, and it's constant, okay. So for that particular region, in the stratosphere, T is constant, as I just mentioned to you. Okay, so that means that my equation then becomes something like this, okay, minus G times RT, and I have DH. And note what I'm going to do now. This is all constant. This is constant. So now I can go and I can integrate on both sides. If I know a point, let's say P1 to P, uh, P2, and H1 to H2, and this integration will give you the natural log of P2 over P1. This is the natural log. And this is a constant, so the constant remains outside. And this is a straight integration, so this is H2 minus H1. Okay, so this becomes quite easy, and I could also, I'm always interested in the temperature mainly, so what I could do is I could elevate to the e power on both sides, and from here I can show that my relationship of my pressures 1 and 2 are given by the following equation: minus G RT H2 minus H1. So this is, at the end of the day, this is the equation that you care for and you want to use. Now, there's a couple of more things that are very interesting that we can also do. We also know that, since we know that P1 is equal to rho 1 R1 T1, and we know that P2 is R2 P2 is equal to rho 2 R2 and T2. This is from ideal gases. Okay, so if I check now my equation and I have P2 over P1, I can immediately see this is air, so air is actually the same value, and in the stratosphere, T1 is equal to T2 is equal to T. This is because we are working in the stratosphere region. So then my whole equation becomes R, I can write this down, rho 1, R1, rho 2, R2, T2, divided by rho 1, R1, T1. Okay, I'm taking these values and plugging them inside here. And I already showed you that this was actually equal to this, E minus G over RT H2 minus H1. So these are constants, so these go away. So basically what we are saying is in the stratosphere, only in the stratosphere, what we're going to have is P2, P1 is going to equal to rho 2, rho 1, and this is going to equal to E minus G over RT times H2 minus H1. So what this is basically saying is, if I knew my initial height, let's say sea level, where I know all these properties, and I want to, well, in this case will not be sea level, right? So we have to start a starting point, and let's say in that plot that I just gave you, I know at 11 kilometers, right there, at that point right there, that can be your H1, and maybe I'm interested in finding that H2 right here. Okay, maybe I'm interested to know what are the properties of H2. If I give that value H2, what will be the properties of my rho? So I can find these values from, if you found these values and you knew all these values, you can find this other, you can find the unknown values that you're looking for. Okay, so this equation is very, very important. It's very good. There's many aspects of it. Only for this and I'm writing down again. Only for this region, stratosphere. Only for that region. You can show that first of all that P2 P1 is the same as rho 2 rho 1. That's one relationship that's very useful. The second relationship that will be very useful is knowing that P1 E, the exponent of G over RT, the H2 minus H1. You could also say rho 2 is equal to rho 1 E to the minus G over RT H2 minus H1. So we can use these equations, but this is where these tables come from. Okay, all those tables, the information I gave you actually comes from these tables, and this is what you can possibly use. You can probably what you can use. Now let's move on to the more complicated region. What happens when we have a gradient layer? In the gradient layer case, that's the case of the troposphere. We are talking about this region right here. We are talking about this region right here. Okay. Now, for this particular region, now things get a little bit more complicated because my temperature is not constant. Actually, what I know is that my temperature is equal to T1 plus A temperature T2. times h2 minus h1. Okay, this is the slope of this line. This is the slope of this line over here, and that slope is nothing else than A is defined as delta T divided by delta H, and this is called the temperature lapse rate. Temperature lapse rate. Okay, and so we know this, and from here I can solve for delta H. Delta H is equal to 1 over A times delta T. Okay, and now you can immediately know what I will be doing. I'm going to go ahead and start with this equation again, minus rho G delta H. You see, this is the same, so I'm going to plug this inside here. And there also another variation, I just gave you this earlier. If I divide both sides by P, okay, minus G RT dH. So I can plug this inside here, and you find this is dP over P is equal to minus G sub 0 RT A dt. Okay, so now what I could do is I could go ahead and integrate on both sides. dP, sorry, over P will equal to minus, and I am so sorry with all this derivation here, but it is important that you understand the consequences of what we are actually trying to do here. So I can integrate here from P1, P2, and I integrate this from T1 and T. Okay? So if I did this integration now, the integration looks kind of similar to what I had before. P2, P1 minus GR times A, natural log of T2, sorry, there's a 2 missing there, and T1. And what I could also do is, again, I could go ahead and elevate to the exponent. And we know the exponent to the natural log is equal to what's inside here. So we could show that P2, P1 is actually equal to T over T1 to the power of G over R times A. Okay. Also, just knowing from our previous relationships, we can, from the ideal gas law, if we just compare the ideal gas law, P2, P1, this is rho 2 R2 T2 divided by rho 1 R1 T1. Gases go away. So now your relationship becomes rho 2 T2 rho 2 rho 1 T1. Okay, so I could also say if I wanted the relationship of rho 2 and rho 1, then I can basically divide this P2 divided by P1, all of this divided by T2 divided by T1. And so just doing a little bit of algebra here, we found what this guy was. we found a relationship for this that is actually is equal to uh, T2 over T1 minus GR times A. We know that relationship, so we're going to plug that relationship in here, minus GRA, and then this is nothing else than T2 T1 minus 1. So from this particular relationship, if we combine all the terms, what you can show is that if you want a relationship of rho 2 rho 1 is equal to T2 over T1 minus G over R times A plus 1. Okay? And for air, you can show, and for the stratosphere, you can show this is equal to 0.0065 K over meters. So you know that relationship, that value is given. And the equation actually becomes a little bit crazier in how you evaluate all these terms. But the one way you do these problems is you have your problem, right? So you go from here to here and here. So when you start this, you're going to start right here. Why? Because you know the value there. You know this rho 1, you know your P1, and you know your temperature 1. This is the values at sea level, okay? So what you're going to see typically, I'm going to use SL for sea level. So anytime you see SL, refer that to sea level, okay? So from here, I can use this relationship, the last relationship I just found, to find my rho 2 and my P2, okay? That relationship in that location will look like this. To find rho 2, you can just say rho 1 multiply T2 over T1 minus G over RA plus 1. And then P2 would be P1 multiply T2 over T1 minus G over R times A. Okay, so sorry, this is this value right here. Okay, so now that we know that value, we can use that as the beginning value for this next region, that typically this is where your plane is actually flying. So it's a two-step process. This is step number 1, right? Where you go here to here, and then this is the location of your plane. This is where your plane is flying, and this is where you want to find all your properties at, okay? And then to find your properties there, then you know everything is constant, and we go back to our previous equations where we can say at that location, I know that my rho 2 will be rho 1 multiply e to the G over RT multiply H2 minus H1. This H2 is this distance right here, okay? So now when we start this equation, we reset this to H1, and this is my H2. In this location, we'll go from 1 to 2, okay? Now my 2 becomes 1, and I want to find it at my location 2. And then if I want to find my pressure at 2, then it's the same equation, very similar equation, if you would, multiply H2 minus H1. Again, this is the delta that we talk about for these equations right here. Okay, that is the process that we want to use in our analysis. And the next, you're going to see a couple of examples how this actually works. But typically, if I say a plane is flying at a location then you want to go from here to here, from here to there. And typically, it's a good idea to have these values handy. And what I would like to do is, I would like to invite you to actually do these calculations by hand, um, and to be able to show that actually, indeed, the values that you get in these tables are the values that we use. So this basically will conclude. We will from here we will move on to do uh, one or two examples to understand all this. But this wraps up the theory part of the atmosphere.